Bismillahirrahmanirrahim. Transport layer protocols. In this chapter, we will look at UDP and TCP. Transport layer. We looked at IP layer before this, and we saw that in the IP layer we have, you could say, addressing. Okay, so just to see how it works, we have the network model, so we have the physical layer first. At this level, we have the bits being sent, literally zeros and ones. Okay, this is how the information the actual physical flow of information is taken care of at the physical layer. Then we have the MAC layer, or rather the data link layer, which consists of the MAC and LLC. This layer was responsible for access control. We are sharing mediums, and when we share mediums, how do we make sure that every device follows a certain set of rules to avoid hitting the packets of other devices? So it was responsible for access control. The layer above it is the network layer, or as it is famously known, the IP layer, because its IP is mainly the protocol that we use for moving packets from one end to the other. But for the sake of propriety, we could just say the network layer. At this layer, we're looking at addressing, routing, how do we move the packet from one place to another, routing. At this layer, transport layer, we are looking at the reliable delivery of information. Okay, reliable delivery of information using TCP. We also have UDP, but transport layer is mainly famous for TCP. When we are sending the information using IP from one source to a destination, the information flows and goes to the other side. It is possible that we are having more than one application open at the source, and this could be, all these four applications could be communicating with their counterparts or similar applications at the destination. So you and your friend could be communicating using Skype. You could be downloading something from your friend's machine. You could be exchanging information using emails and doing various other activities. So in this way, you could actually be having all four programs accessing or communicating with the four programs at the destination. If we use IP, because it's the same machine, when the packets from these four programs go down, they will all come out as a single stream of packets that goes all the way to the destination. The destination address for all the packets from these programs is the same IP address, because they're going to the same destination. Now the question arises, how can we differentiate these packets? How can we know what application this packet is for? Okay, For that purpose, we have something called port numbers. Port numbers. Okay? And these port numbers will tell us which application this packet is meant for. So there will be no confusion at the destination. This is one of the important things that the transport layer does out of the other important functions. So we have TCP and we have UDP sitting at the transport layer. A packet coming from the transport layer goes down to the IP layer, gets an address, then goes down to the data link layer where it will wait for its turn. It could be CSMA-CA, CSMA-CD. You could use various different access protocols. And once the medium becomes available to it, then it will use the physical layer mechanisms to transfer the information to the other side. So the transport layer protocol usually has several responsibilities, which is one is to create a process-to-process communication. Okay, so as we saw in the example, we have the application that communicates to the TCP layer or UDP. And this should go all the way up to the respected application on the other side. So it is process to process. Could be anything. Could be your web browser. It could be Skype. Could be anything. Okay. So it's going from here to here. So and we're using port numbers to accomplish this. And we will see in the other slides how we do that. So we are doing multiplexing and demultiplexing, which means all these applications will send information to TCP. TCP will make the packets and then they will be sent over to the other side. Again, they go all the way up IP and then TCP. And then at this point, TCP will, based on the port numbers that it has received, it will forward the packets to their various applications. So port numbers play a very important role in TCP. So the information, when it is flowing between a source and a destination, when the information is flowing from a source, so this is the source and this is the destination. So this is the IP layer. So it doesn't just stop here, right? And it doesn't start at the IP layer. It starts above at the applications, goes down to TCP. Based on what application you're using, you will have the port number assigned. So if it is, as we saw in the other chapters, if it is FTP, it would be either 21 or 20. If it is HTTP traffic, it will go to port 80 at the destination. Okay? So by using the port numbers, we are actually multiplexing different information onto the same TCP and IP layer. And then when it goes to the other side, based on what port number it is, it will then go to the different applications. So this is multiplexing and demultiplexing. So here are some of the common known port numbers. We have 20 and 21 for FTP, 23 for Telnet, 25 for SMTP, short simple mail transfer protocol, 53 DNS, 67 DHCP, 80 HTTP, and 111 RPC. Which means that if a source sends a packet with this number, with number 20 in its destination port, at the destination, this packet will only go all the way to port number 20 and nowhere else. No other application, only to that FTP application. Now we will look at the first protocol, which is UDP. UDP is connectionless and unreliable, which means if we have a source and a destination, and if we are using UDP, UDP will simply send the packets and forget about it. We don't establish any connection like TCP. We don't do any handshake. We don't establish any connection. We simply, if we want to send something, we just send it, make a packet out of it, send it, and forget it. We also don't worry about acknowledgement, so it is unreliable. So we don't, if we send a packet, there is no acknowledgement received from the destination. So now the question arises, if UDP is so simple, why do we use it? UDP is mainly used for applications that are delay sensitive, right? So UDP, it will be used for delay sensitive applications. And what do we mean by delay sensitive applications? If we were to wait for an acknowledgement from the destination, it would cause a delay to existing packets. For example, in TCP, until we receive the acknowledgements for some packets, we can't send the other packets, right? So in this case, if the acknowledgement is still coming, until then, we can't send these packets at the source. And this will cause a delay. A good example of this is your video conferencing that we do on Skype. If the connection is bad, the screen hangs up, the video stops. It freezes. And that's not good because it spoils our experience of that video chat. So delays in delay sensitive applications are not good. What are delay sensitive applications? They are mainly real-time, interactive applications. Okay? Real-time, interactive applications. Which means if two people are talking on Skype, that's real time. That information will become difficult to understand if there are delays in it. If you're talking to your friend on the phone, if there are delays in the conversation, it spoils the whole experience. And then you say the connection's bad, and then you hang up and you try calling back, just hoping the connection improves. So that's real time, okay? Both sides are communicating at the same time. So delay is to keep a minimum delay in this case is very important. And similarly, interactive, okay? If I am interacting with something online, I want to have a minimum delay. So it is for these applications that UDP proves to be useful. Because UDP is not fussy about flow control, error control, congestion control, it will simply take a packet, send it, and hope for the best. But this sending of the packet means it is immediate. There's not much delay for the packet. The packet doesn't wait long in buffers. It just goes. And this is why UDP is useful. Now looking at the UDP header. In UDP we have 8 bytes of the header and the rest will be data. So the minimum size of a UDP packet is 8 bytes to 65,535 bytes. That's the maximum we can go in the size of a UDP packet. Looking at the header carefully, we have a source port number, destination port number, total length, and checksum. We have each field of 16 bits in size, or 2 bytes. So the total is 8 bytes. Now, although we have a total size of 65,535, in reality, if we are using IP, we can't use that size. It has to be less. And that is because an IP packet, the size of an IP packet, the maximum size of an IP packet is the same, 65,535. So if this packet is coming from above, then we will have the IP header and we will have the UDP packet. So if this is 65,535, then there will be no place for the IP header because the total length for IP packet is also 65,535. So this is why if we are using UDP along with IP, we can't have a maximum of this. It should be less. At least 20 bytes less, or more optimally 60 bytes, so that we can accommodate the IP header, all of it, including options. Now this example tells you how you can find out the contents of a UDP header. And we know that in the UDP header, each field is 2 bytes. So that would be 4 hex digits. So the first will give you the source port, right? This will give you the source port. This will give you destination port, total length, and checksum. This is the answer. So the first is a source port, which is 52,100. The destination port is 13. Time and date. The total length of the packet is 28 bytes. And the data length will be 28 minus 8, which is the UDP header. So data will be 20 bytes. So when we talk about UDP services, we look at the different services it can make available. It does provide process-to-process communication because it makes use of the port numbers as well. However, the services are connectionless. It does not provide any flow control. It does not provide any error control or any congestion control. Encapsulation, decapsulation is very rudimentary in TCP, in UDP. So we have already spoken about what applications prefer UDP. Now these are some of the well-known ports. Again, we have discussed this as well in the previous slides. Some additional, we have 7 for echo. It echoes what we just sent. 9 will discard any datagram that we receive. 11 will show the active users. 13, contacting at number 13 will show us the date and time, and so on. There's also another place where we can use UDP packets, and this is when we don't need to send more than one packet. So if we have a client and a server, and the client wants to know the DNS of the server, if it wants to know the domain name for the server, it will send a DNS request. Okay, it will send a DNS request to the server, and the server will respond back, and the port it will use will be 53. Okay, so the source will send a packet, DNS request packet, to the server at port number 53. When we are sending information to a destination, it is good to know their port, and it is good to know the specific port. So if we are using HTTP and if we are a client server, if a client is contacting the server, an HTTP server, it will send the packet only to port number 80, and not to any other port. If it is an FTP transfer, then the client will only send the FTP request to port 20 and 21 and not to any other port. So in this way, when a request comes for the first time to the server, when the server looks at the port number, it will know exactly what the client wants, and it can service the request. In this case, the DNS request can be accommodated in one single packet. And also the response that comes back from the server will also fit in one single packet. So we don't have to worry about fragments on the other side. We don't have to worry about joining packets to make one bigger packet. And in this case, we don't need sequence numbers, we don't need acknowledgement numbers. Even if the single packet gets lost, we can always send it again. So this is another place where we can use UDP as a transport layer service. In this case, in this example, we discuss how an application like SMTP or email cannot make use of the services of UDP. This is because emails can be big in size, so they may have to be chopped into smaller fragments, which means we need to have flow control at the other side. So in this case, bigger packets, we can't make use of UDP because we can't reassemble or join the packet at the other end. The same thing is for a large text file that we may be downloading from the internet. Again, in this case, we need TCP because the file is big. There is a number of packets that will come that we will have to join to make that large text file again at the destination. And now on the way, we don't want these packets to get lost or corrupted. Otherwise, we won't be able to join the file back at the destination. So for this purpose, again, we can't make use of UDP. Instead, we use TCP. This example is about Skype, which we have already discussed. The next protocol we look at is TCP, and this we will begin in the next video.